phase variables. This is not but we make it formal by just with this notion of a phase variable. In ZX, this means that rather than working with just those angles, we make it into a Z module. We just add in this syntactic element. Things like ZW and Z8. These variables are formal variables inside the algebraic structure that exists on our nodes. They need to be evaluated before we get back to having a simple diagram. So as before, we need to specify what alpha is before we get back to a universal ZX diagram. Here's an example. If I evaluate alpha to be pi, everywhere in my diagram, normal ZX again. So that's not going to matter. OK. Pause. Bang. Bang boxes represent repeated elements of our diagram. So I've got a normal ZX diagram, but I've added in the node bang1. And it's pointing towards the green node, indicating that green node is inside the bang box. If we want to expand the bang box n times, which means have n copies of what was inside it, then we copy everything inside it and then just remove the bang box. Again, an example. I'm going to expand bang1 twice. So I want to end up with 2 copies of the thing that bang1 is pointing at. A simple diagram again, similar to phase variables and evaluation. Going to be time for some actual categories in a moment. Any questions?
You said copy and delete. Is that explicitly part of the operation? Like, is there?
Ignoring all semantics of the nodes, copy syntactic chunks of the diagram, and then complete with their edge connection. It is a precisely, there are ways of doing this precisely formally, and they are equivalent to this informal version. Particularly for all of the examples I'm giving. Alex would talk, it's like ZX but uses a ring rather than group structure. This is for ease of examples to clutter things. And similarly, ZW has nodes that aren't spiders, which means you need to be a little more careful when you're trying to copy, because you can end up with sort of breaking the correct arity on a node. So ZH doesn't have these problems, but these problems are surmountable. So category of diagrams ZH, well, open hypergraphs built from these nodes. This is an H box. It's square. My boxes have complex numbers on. My round spiders do not. It has an interpretation. I remember from sort of slide 2, the interpretation points to the category we really care about. We're still using the square bracket notation you've seen throughout the week. How do we add phase variables to ZH? Oh, nope, too far. We do this, so before, by changing the underlying algebra. Rather than just having complex numbers on the nodes, we now have complex polynomials. And an evaluation for x, and I get out a simple diagram that no longer has a. How about adding bang boxes? Well, as before, we added a new node type called bang. For now, we're going to stick with just adding one, explain why later. And it's got directed edges which say what's inside the bang box, and we call this category of diagrams ZH bang. Similarly to phase variables, it takes us from diagrams. Copying something and then copying nodes and then evaluating all those nodes in the same way in our commutative square. So we're going to try and make that interpretation structure work with everything else. There we go. It's actually quite easy for when we've got phase variables, because we can do currying for the bang boxes. Well, what is the interpretation of this? Well, once I've told you how many times to copy the bang box, then I can get a matrix. And of course, this is, hopefully you can see where this is going towards. We have a commutative cube. The horizontal lines are the assignation of natural numbers to work out how many times to copy your bang box. Or the vertical lines are evaluation of phase variables, and all the lines into the board are interpretation. So that's our framework. What is the problem that we're trying to solve? It would be fantastic to know when 2 ZH diagrams with phase variables and bang boxes have the same interpretation. And if you can solve this, then you can solve all of quantum computing. So we're going to have an assumption. We're going to assume that we have good knowledge of interpretations of just ZH without the bang boxes and phase variables. By good knowledge, I just mean we're considering this cheaper enough that we want to be doing that instead. On our diagram, we are interested in that brown functor there. We want to know when 2 morphisms in the top left category coincide under that interpretation functor. we're assuming that we have good knowledge of what's going on down here. We're going to assume it's also going to be cheap to do the assignation and evaluation just inside the diagrams, not inside the matrices. And so what we're interested in are these two arrows here. We're going to try and find some properties in these areas such that we can pull the information we have, or at least the cheapness of performing the task of that blue arrow all the way up to the brown one. So first area we're going to be looking at is this right-hand side here. Matrices of complex polynomials and just complex numbers. So related problem number 1, I first encountered this in numerical analysis, some polynomial, and knowing what the degree is, then I can determine what the polynomial is. It's not too hard to, if I can finitely sample a matrix of complex polynomials, then I can determine what those polynomials actually are. Theorem in the paper, if I've got two ZH diagrams with phase variables, then I can use this finite sampling to determine whether the interpretations coincide. Note that you can work out from a diagram directly how many times you need to do the sampling. So that was this arrow here. So, mind you, this pointer? Good. We're interested in two diagrams here when they coincide under this functor. We're assuming that this is easy to do because that's common diagrams. This is cheap, and we have a finite sampling property here that allows us to complete this square. So, related to problem number 2, actually to give it to us, we're now going to be looking at this region here. Related problem number 2, chains, which is linear algebra, the d+1 steps. If I'm going up a dimension every time and I'm capped above in my dimensions, then my sequence stops. So W is my ambient space. This is the longest chain. This is the longest increasing chain of subspaces I can have. Well, I have something that looks a bit like sequences. This currying action gives me, depending when I put in 0, 1, 2, 3, etc., gives me a sequence of complex matrices, which I can interpret as, well, I can then coerce this problem. Not gonna lie, this is where quite a lot of the paper is how to make this problem here look like the problem we're dealing with. But I can coerce a problem to look like a sequence of subspaces that is either increasing but then stabilizes at some point. The theorem this gives us, and you don't really need to mind about what the equation is, except that the top one has, if I know this equality for all n less than or equal to some d, then I know it holds for all n. This is another sort of finite sampling property. Again, we can work out d syntactically from the diagram. You're not going to be doing this forever, with the caveat. If I have two bang boxes sort of really right next to each other, then it can essentially make D unbounded. So that is the caveat and why we're only using one bang box at a time. So again, we have two diagrams here. We're trying to see where they coincide under this functor. This is easy to do. We're assuming this is cheap, and this was where our finite sampling property we've just shown exists. Right, putting it together is the main theorem of the paper. If we have two diagrams in ZH that have bang boxes and phase variables, then we can perform a finite number of samples to determine whether they coincide under the interpretation. This does extend to multiple bang boxes. Remember, we have the caveat, so that's the details of that are in the paper. But most of the time, it works just fine. So this is our categorical framework. Any questions at this point? Yes?
I think at least which arrows are the hard ones.
Which arrows are the hard? So this interpretation here is hard and of interest. This interpretation here is what our first theorem was. This interpretation here is what our second theorem was. They were viewed as hard before we got the finite sampling theorems.
After you have polynomial interpolation.
So essentially, nothing remains nothing is hard anymore, providing you want to do this finite sampling. It may be the case that you need to do so many samples that it becomes more expensive to do that than to sort of slog through the actual interpretation. But based on the assumption that this thing is cheap and that we have few finite samples to do this, then this thing, I've lost it, this thing here that was hard is now viewed as easy, and that was our target. Jules?
Your assumption that the ZH to mass is cheap, don't you have to use quality products too?
This is expensive, but I'll get into why I'm justifying this assumption just after the recap. The bit that says why we care is why I'm assuming that I do have some knowledge here. So, recap. Bang boxes and phase variables were already in the literature sort of as distinct things. We set up a compatible categorical framework for both, for bang boxes, phase variables, and interpretation. That was our cube. We identified what the problem was inside this categorical framework. There we go. Found things in related fields and essentially have tried to lift those properties. Right. Why should we care? And also justification for why I seem to have so many ZH theorems lying around. ZH equations lying around.